Hello everyone, welcome to this video. My name is Emerson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm gonna show you how to increase the spatial resolution in ERA-5 skin temperature data. It is one of the valuable climatological products available in the Earth Engine. So, as you can see here, this is the original land surface temperature or skin temperature from ERA-5 product, and after downscaling process it's increased to 1 kilometer. And here you go. In this tutorial I'm going to show you how you can do this process easily using Earth Engine platform using regression technique. So make a new code editor environment in your account first. So now I'm gonna call ERA5 and modify temperature in the first step. Make a variable for ERA5 data. In the first step, unlike the other tutorials on my YouTube channel, you don't need to define the region of interest first, but you must define two different variables, one for ERA5 and another one for modis product. ERA5 equals to, through the search places and dataset, go to find ERA5 land daily aggregate products. Land daily aggregate products is available here, ECMWF Climate Analysis. If you click on here, you can have access to the data description. It is one of the most valuable products for the remote sensing for earth science and climatological studies because it is available since 1950 with daily temporal frequency that is very valuable. So its spatial resolution is around 10 kilometer, but I'm gonna show you how you can increase it from 10 kilometer to 1 kilometer. That could be very useful and beneficial for the earth science studies because when you have higher spatial data, you will be able to monitor the temperature variation even for the time that 1 kilometer data didn't exist. So now import the product into the code editor environment. As you can see, we have it as an image collection. Assign image collection to the ERA5 and then make a temporal period in which you want to do modeling based on. So first I'm gonna make two variables as time start and time end because first of all I'm gonna make a model between ERA5 skin temperature and modis LSD products for in a period of time. We want to do modeling for a period of time that is correspond or same between ERA5 and also the modis data. For example, the modis data is available since 2001, mid 2001 or early 2001, depends on the satellite sensor, but and also it is available until 2020, the day I'm producing this tutorial. And as you can see here, we need to select a period of time in which both of data, original one and the predictor, both of them be available. So here I'm gonna select a period of time, for example, from 2010 to 2020. This is a period of time ERA5 and modis LSD, both of them are available, 2010 to 2020. 10 years data is a good thing to train a model based on, and then we can predict LSD high resolution in the ERA5 product. So filter date limited started from time start ends or ended to time end. So now there are several bands under ERA5 product image collection. If you go to the data description and open it into a new page, then you can see all the information easily. Go to the bands. In addition to the spatial resolution, the bands with descriptions are available. The target band is the skin temperature. This is the target band I'm gonna increase the spatial resolution based on. So the skin temperature copy the band name and back to the code here. .select is a function allows to select the target band. Here I'm gonna select the skin temperature for the period started from 2010 to 2020. No need to define filter bound because coarse spatial resolution data doesn't have framing structure such as Sentinel and Landsat data. That's why we skip the filter bound here. Make another variable for the MODIS product. Let me to remove the 5 from here because I'm going to use the variable name with a simple structure. MODIS equals to go to search places on dataset and type MODIS temperature daily product. MODIS temperature and emissivity daily products from Terra and Aqua satellites are available. The main difference between Terra and Aqua is the start date. The Terra data available since 2001 or 2000, and also the Aqua is available since 2002 and 2000 or 2003. Exactly here you can see the Terra satellite data available since February 2000. And if you go to the data description for the Aqua product, here you can see it's available since the July 2002. So there is no any other difference. So here the MODIS equals to, I'm gonna use the Terra product here, the second image collection, assigning to the MODIS variable. And then, as you may know, if you go to the data description, you can see a couple of bands available in the MODIS product with 1 kilometer spatial resolution. But the target band correspond to the skin temperature is the land surface temperature for the day, because both of them is taken or produced by day. LSD day, just copy and paste it here. As I mentioned earlier, that select LSD day allows to select the target band. That filter date, limit your data to the same temporal period starting from time start and ending to time end, just like that. So let me make a print from ERA-5 data and also the MODIS to see if there is any problem or not. Print is a useful function, allows you to check the workability and applicability of the code and helps you to understand if any syntax error exists or not. So as you can see, around 3,600 images available for 10 years and also from ERA-5 ECMWF. So then I'm gonna check the bands, but as you know, there are a large number of data in the right panel, and also it reduces the speed of processing. That's better to limit your data to the lower number because just we want to have a simple check. For example, just I'm gonna show or I'm gonna see only 10 first data from each dataset. As you can see, in the all dates available here, there is one band, it is skin temperature with the metadata, and also this is the same also for the MODIS data, but here we have LSD day with 1 kilometer, and metadata information and properties is also available here. So there it is, 2 variables called, and there is no problem. Just here, I'm gonna say that the ERA-5 is the original data that we want to increase its spatial resolution using a predictor, and predictor in our model is the MODIS data. So let me to have a visual check. Map.add layer, as I mentioned a lot, is a popular function in the Earth Engine, provides good facilities for the visualization. First, I'm gonna have a quick look on ERA-5, the first data in the ERA-5 collection, and no need to clip it based on a specific region, and then leave the visualization parameters empty, and the layer name is ERA-5. and use the false at the end. False help or avoids from automatic visualization that highly reduces the speed of processing. Now, when you use the false, then you will have higher speed of processing dealing with the Earth Engine Code Editor environment. So that was for ERA-5, replaced with MODIS, and also the layer name returned to the MODIS again, just like that. Run a code again and back to the Google Map. Here, using the Google Map, you can see the first image in the ERA-5 and MODIS collection. As you can see, this data has a global coverage, meaning that you can use this tutorial for all around the world and not only limited to one specific region. So this is the ERA-5, and I'm gonna increase the contrast by 90% of value. This is the January 1st ERA-5 data skin temperature. As you can see, the water bodies has higher temperature. It's because of the time of the year. In the January, the weather is cold, and also on in the surface, most of the covers and also most of the phenomena, including water content such as vegetation and also the lake, has higher temperature. And one thing is important, and also it should be noted that the ECMWF data is not direct estimation from the satellites. It is one of the assimilated products that is combined. It is a combination of the results from satellites, model, and also other complementary data. And it is not affected by the cloud cover that is very awesome in the remote sensing studies. You will have access to one temperature data with daily frequency since 1950s, and also without cloud impact. That is very wonderful in the process. So this is about the ERA-5 data, and also this is the MODIS temperature data. As you can see in the MODIS product, there are a lot of unknown pixels, there are a lot of missed pixels, and also the missed pixels was cloudy one, and only clear sky pixels remained here, that you can see both of them here. And also these are clear sky pixels, and I'm gonna do a model or make a model based on available pixel or clear sky pixels with the skin temperature we have. And clear sky pixels varies from one time to another time. Maybe for tomorrow or the other days, this area covered by the clear sky pixels, but in the day or in the date I'm doing visualization, most of the regions covered by the cloud. That makes sense because it is a winter, and most of the regions covered by atmospheric circulations, and also the cloud coverage, and on it goes. It's beyond this tutorial. So back to the code. As you can see, we have LSD day from MODIS and skin temperature from the ERA. This is the original product, and this is the original temperature data that we want to increase its spatial resolution from 10 km to 1 km. But here we have a MODIS, that all the cloud covers must. It is LSD. There is a linear relationship between the LSD and the skin temperature, and it could be a good predictor using regression relationship that helps us to make a model based on close relationship between these two kind of variables. They are almost same criteria from two different sources. One of them is assimilated, and another one coming from the satellite estimation. So now we're gonna use the predictor to improve the original from 10 km spatial resolution to 1 km. But before modeling, we need to actually make a new collection in which for each date, one ERA-5 skin temperature and one MODIS LSD date is available in a single stack layer for each date. So let me to make a bigger space here, and same time you can see the differences between ERA-5 and MODIS temperature. And one important thing is that when we combine ERA-5 and MODIS data, you can have a final product with the MODIS and ERA-5 properties together. The spatial resolution comes from the MODIS and radiometric information comes from the ERA-5. In that case, you can have a product, you can have access to improved MODIS product since 1950 to now. And also it's very, very valuable for your studies. So now I'm going to make a single collection, as I said, having ERA-5 and MODIS together. Now I'm going to join these original values and also the predictors in a single image collection for each date separately. So now I'm going to use join process here, Earth engine dot join dot inner. The inner join is a kind of method that helps us to find and collect the data for corresponding dates from two separated collections. So make another variable as filter Earth engine dot filter dot equals. Here the equal filters including different arguments, left field, right value, the right field, and the left value. The left field and right field are target argument here, and also the left and right, meaning that we have two different collections. One of them is ERA and one of them MODIS. For example, ERA is left and MODIS is right. Two collections and we have two fields, left and right. The correspond field or correspond metadata that we want to do joining process based on is the system time start. So I'm gonna make a filter in which system time start is equal between the right field and the left field. And then I will show you how we can combine join and filter and images in a single expression. Just be patient here, and now assign the left field to system time start, right field system time start. There it is. Get rid of the others, and now here we have a filter. So the join and filter. Now I'm gonna combine, I'm gonna merge or join MODIS and ERA-5 based on same system time start and also using joining function. Make a new variable, join collection equals to Earth engine.image collection. First, I'm bringing all process under image collection format, and then bring join here and dot apply. Apply the join process on two images. One of the collections is primary and another one is secondary. For example, it is optional. ERA-5 is, or ERA here is primary, and secondary could, for example, MODIS. Based on what condition we want to join these two together? Based on same or correspond system time start between two collections. So here, based on a filter, I'm gonna make it. So now print my popular function join collection. The join collection, but as you know, there are thousands of images for this period of time, and printing 3000 images reduces the speed of processing. That's why I'm highly suggesting you to make your code simple by limiting the result to only 10 first elements. That's highly helps you to speed up your processing. In the right panel, you can see we have a feature collection. For each date, we have a feature with two properties. One of them is ECMWF ERA-5 data, and the second property is MODIS LST data. But these are in feature format and property style. I'm gonna convert it from the feature collection to image collection, and I'm gonna have the LST bands from ERA-5 and MODIS as the image, not as a metadata here. That's why I need to make a function. So make a new variable as final collection equals to get join collection first, bring it into a loop, make a function, each input image consider it as an img here, and now make different separate variable for each data, ERA and also for the MODIS. Here we have ERA-img equals to from each input image or from each input feature img.get. Whenever you want to select something under properties format, you have to use get. So .get, as you can see, the primary parameter was ERA. From primary, get everything, convert it to the image, just like that. Another variable after ERA is MODIS image equals to earthengine.image from each input image that select secondary, just like that. The ERA and MODIS, both of them separated as an image format, and also now I'm gonna bring them under a stack structure. But before go further, we need to convert the MODIS range of values from original range to the Kelvin range. If you go to the data description for MODIS under band, you can see there is a scale value 0.02 that should be multiplied on MODIS data to return MODIS with Kelvin format. So now the secondary, including the MODIS data, here multiplied to 0.02. Now we have ERA-5 and MODIS data for the corresponding date and also with Kelvin form, with Kelvin units. So this is for ERA-5 that multiply 0.2, but seems there is something wrong. Missing semicolon, that's secondary. Oh yeah, we had one extra parenthesis here and removed it, and here a new variable as a stack, earthengine.image.cat. I'm gonna bring two separate variables under same image or layer stack, including ERA image and MODIS image. Another variable, no need to another variable, just return the stack layer and print collection now. In the new image collection, as you can see, the format is image collection, and also we have different elements here, each element including two different bands. One of them is skin temperature from one of them is a skin temperature from ERA-5 and another one LST from the MODIS data. So that works very well. So the collection is ready now, but we need, as we want to make a model between ERA-5 and MODIS, it is very important to actually resample ERA-5 from 10 km to 1 km. I'm gonna resample ERA-5 pixel size actually here. So now I'm gonna make a new variable as ERA resample equals to get ERA-img and then dot resample first, that resample, and then reproject it based on a CRS and a scale value, coordinate system EPSG ERA-4326. This is a code that globally we use for WGS coordinate system, WGS 84. And a scale equals to 1000 meter or 1 kilometer. This is the error resample that I want to have error resample next to the MODIS image for each date. So, and also the stack layer including error resampled with MODIS ing. So, the CRS of map projected could not be parsed. So, EPSG, the writing was wrong. Yes, now the problem is solved. So, we have an image collection that's including the MODIS and ERA-5 for the MODIS and ERA-5 product with a resampled format for the corresponding date under a layer stack. So, in the next step, I'm gonna make actually a regression model based on 3000 training data I have. So, back to the code here. We want to do modeling, a regression modeling. So here, make a new variable as model equals to, so bring collection first and then reduce it, first engine.reduce. One of the reducer is linear regression. When you want to use linear regression between original and predictor, you must have a constant in your dataset. The constant value is missed here, but we can add it. A new variable as constant equals to earthengine.image.constant. I'm gonna have a constant image with value 1 for all pixels. So I'm gonna have the ERA-5 as an original product and constant here with the MODIS ing or the predictor. So the stack layer now included the constant next to the error resample and MODIS images, because the constant or having the constant is the necessary for linear regression. So linear regression. Here, two arguments we have. The first is the number of x. So the x including error resample and constant based on the data order. X equals to 2 and y or predictor is the MODIS ing. This is only one image. So the combination or the order of value is 2x, 1y. So print the model. Print regression model. There is one image. The image including coefficients and coefficients including the gain and slope, but it has two dimensions. It has array structure, but I'm gonna extract the gain and offset image from multi-dimension data here. Now I'm gonna have gain and offset. The coefficients is the actually the main parameters we want to use for the predictions in the next step. So because the model is trained based on ERA-5 and also the MODIS data, and the gain and offset shows that how much they are different, actually explaining the differences between the original predictor, between the original variable and the predictor. So from model.select coefficients, just like that, and as it has dimensional structure or array structure, that array get is the function allows to select the first dimension as a gain image. So the offset equals from coefficients dot array get the second dimension, just like that. So now we have one image for gain and another image for offset that explaining the differences between the original variable and predictor together. So now we want to do prediction in the next step using a linear equation. For example, as you know, in 1970, for example, in 1970, we had no 1 kilometer data for a skin temperature, but ERA-5 products with 10 kilometer for that day is available. We have a gain and offset that explaining the differences between the MODIS and ERA-5 data. Now I'm going to apply these factors, coefficients on the, for example, ERA-5 product in 1970 and have to get access or to achieve 1 kilometer temperature data for that time. That could be very, very beneficial for the climatological studies and also climate impacts, and also to study about the climate impacts on different phenomena on the Earth's surface. Now I'm gonna make a new ERA-5 product for example, 97 equals to the first image collection we had. This is the first image collection that filter date. I'm gonna call this data for 1970 to 1971 for 1 year, and the variable I want to apply the gain and offset on is ERA-5 skin temperature. Select ERA-5 skin temperature here, just like that, and then make a new function, make a loop to apply the equation on each available skin temperature data for 97. Each input image considered as an IMG here, and now the predicted temperature equals to from input image dot that includes the skin temperature. I'm gonna make a linear equation. The input or x multiplied to a and add to b. So multiply a is gain and add is offset. Here we go. The result including predicted temperature and the original temperature is also IMG. Finally, function returns the original temperature with predicted temperature. The original temperature has 10 kilometer resolution and the predicted one must have 1 kilometer with the properties of input images. This is very important. Save your code now and do the visualization using map.addLayer. Map.addLayer, couple of arguments. I'm gonna see first the ERA-5 for 9070. The first I'm gonna see the original product, that is skin temperature. For the first day, actually, I'm gonna call the data for the first day of the year. It probably is January 1st in 1970, and I'm gonna clip it based on the region. For example, I'm gonna select a region here in Iran, in the northwest of Iran. Using the drawing tools, select a region. You can select everywhere in all around the world. I'm gonna select this region because here I have the water bodies, I have the forest, farmlands, and also the bare lands. It has a good combination of different land covers. Leave the visualization parameters empty now and change the name to, for example, it is original temperature, and shown will be false, and skip the opacity. Use the same add layer structure, but this time for the predicted temperature. I'm gonna have a visual comparison between the original temperature and the predicted one. Predicted. Save your code and run it. So, too many arguments here we have. The geometry is missing. Yes, when you call the clip, you must use a geometry or a shapefile inside. Just like that. Save your code and run it again. There is another problem. Band pattern predicted temperature. It was my fault. Or predicted is better. Try to use simple words in programming. Save it again and run it again. In the layers panel, couple of products available. One of them is original temperature. Let me to increase the contrast using layer setting. Here you can increase the contrast by 90% of values in the screen temperature. This is the original temperature, ranges from 260 to 283. Here I can add it here. If you want to get rid of the stretching process, that's sometimes time-consuming process, you can add the minimum and maximum manually here. The maximum is 283 and the minimum is 259. So we can use this for the predicted value. Although they don't have the same range of values, but they don't have actually very big differences, and also we think that they will have very close range of values. Then it is anticipated to use same range of same minimum and maximum for two products here. So this is the January image in 10 kilometer data, and as you can see in the water bodies we have higher temperature because it is for the January and weather is cold, and also everything including water such as croplands, vegetations, and also the water bodies reflecting higher temperature value. And also here we will have the predicted image. Let me to run it again. This is the original one. Now you don't need to use the actually stretching technique anymore. And also here is predicted value. Definitely predicted visualization for predicted image takes a little time because it is the output of actually a process coming from making a model between thousands images. That's why it's a little time-consuming process. If you want to get rid of the actually visualization, visualization and difficulties related to visualization process, I suggest you to get export. You can use the export function in the Earth engine to download the results quickly and move them into Google Drive, and then you can transfer them from Google Drive to your own desktop software such as ArcGIS Pro or QGIS or any other geospatial software you are using with. So here, let me to show you something happening here, but same time I'm gonna use export to save the time. Export.image to drive is a kind of function helping us to save the results. So the target image is, for example, ERA-5 predicted data. Here the target image I'm gonna save is the predicted temperature. I'm gonna save the first image just like that, and then The description, name of output could be ERA 1 kilometer for 9070, and scale equals to 1000 meter, and the next parameter is region equals to geometry CRS coordinate system EPSG 4326, and also the max pixels equals to 1E13. The next one is the target folder you want to save data in. Could be, for example, the test folder. You can pick any other name you want. So this is the function that allows you to save your result into the Google Drive. So, and also this is the result, but it doesn't have a good contrast because they don't have exact same range of value. So now I'm gonna do increase the contrast by stretching techniques. Definitely the minimum and maximum value will change based on characteristic of new images. There are also some methods helping us to reduce the differences between predicted temperature and original temperature that I can show you in the next steps. Let me to do the visualization first here. As you can see, it's still time consuming. You must be patient when you are dealing with visualization or whenever you want to visualize some results from a modeling process in the Earth engine. Definitely it takes a little time, but I'm suggesting you to get expert and don't waste your time with visualization in the Earth engine. You can quickly save it into the Google Drive and then open it up into your desktop softwares. So I'm still waiting. But as you can see here, the one thing is missed is that you can see the impact or effects of coarse spatial resolution image into the result. Although spatial resolution increased, let me to increase the contrast. Although the spatial resolution increased, but still we can see the pixel effects because in the model, a model coming from a resampled data, it is okay, but the input, the original temperature, not resampled yet. So if you want to have a more smooth estimation for the output, you must do the resampling process for the before applying model on input data. So the resampled equals to the input temperature img that resampled and then reprojected based on EPSG 4326, and then the scale value equals to 1000. Then we will have less pixel noises or pixel size noises in the results. But remember to use the resampled one for prediction process. Save your code and run it again. Let me to increase the predicted contrast with 90% of values. If you go to the task now, you can see ERA-5 for 9070 with 1 kilometer. The output of model is available to save into your Google Drive. Click on run, and after the tab color turned to blue, meaning that the result is saved, the process of saving into the Google Drive completely done, and you can pick it up and open it up into the desktop softwares. So I'm still waiting For the new range of value, we update it here, and then we can see the final result accuracy. And then in the next step, I'm going to show you how you can increase the quality of the predicted temperature to make it more closer to the original temperature data, because it is a prediction and definitely there are some value differences between the predicted temperature and original temperature. So there are some correction methods that you can apply or use them here to improve the accuracy of predicted values. So seems it still needs time. So we can do the correction here until the visualization process gets ready. So back to the code, and same time whenever the result gets ready, you can see it. And also I showed you how you can save it into your Google Drive. That could be beneficial in case the process of visualization takes longer than usual specifically. So back to the code. Now I'm going to use a correction method. There is a famous or popular correction term for the downscaling process. If you followed my previous tutorial on my YouTube channel, I showed you how we can improve the accuracy of results using correction terms. The correction is an equation like this: corrected image or corrected temperature or any other variables you are calculating. Correction or corrected equals to the output of model or modeled temperature will add to the differences between the original temperature and the model average, model mean or the average of modeled temperature. The differences between these two variables help us to increase the accuracy of modeled temperature. This is what you must do actually to improve the accuracy of the predicted or make it more closer to the skin temperature. So here, just make a new function here, make a new function for the predicted average. Prediction mean equals to, from ERA-5 for 9070, I'm gonna make an average in each pixel using mean function. Then make a new variable for the original, make a new variable for corrected temperature. Corrected temperature equals to, so get ERA-5 for 9070, make a loop to apply the correction term on each existing band. Each input image considered as an IMG, and now make a variable for each term separately. So the original temperature equals to, from input image, select the skin temperature. This is the skin temperature, but it should be resampled before. Yes, because we already did it here. Make another variable for prediction. Predicted temperature equals to, from input IMG, let's select predicted. Here we go. For the next term, we want to actually apply this model or write this equation. The equation index equals to the predicted image dot add will be added to the differences between original dot subtracted with predicted with prediction mean. And also here, the visualization takes longer than usual. That's because of the recording of a screen. When you're recording the screen, when you record the screen and also do the process, something like this, it reduces the speed of processing generally on your system. That's why it takes longer than usual. Here we can see that it's still under saving process, and also we can check it whenever it gets ready. So back to the code, and finally function returned index the corrected temperature with the properties with the property of input images. There you go. Also, it's better to set a actually estimation for the range of values from 260 it was to from 260 to 290, just like that. And now in the next step I'm gonna do visualization for corrected term. The corrected term will be something like this that I showed you already here. We want to get such kind of close relationship that helps you to see the all variations, all the patterns of temperature variations between the original and downscaled products. And also there is no matter here we have a visualization problem because it is because sometimes it happens because of the speed of processing. But here you can see the final results, and also I'm showing you step by step how to do this process. Map.add layer, this is for corrected term. It only includes one image, so we skip the selection part. The first image clipped based on the region of interest, and then yes, this is the range of value, and then click on apply to see the predictions result without impact of pixels. That was related to the output coming from applying model here, but it was under effect of pixels that now is solved after resampling process I showed you in the previous steps. So, and I can use the previous range of values such as 260 to 290. This is the corrected layer. Save it and run it again. This is the original image, and this is the corrected one. It's still in progress and ongoing. You can use the export function I showed you before. You can use yes, here it is. I was looking for a export function that I have used. So you can use this, the same function, but this time for the corrected image. Just replace ERA-5 9070 with corrected one. No need to select. Skip it. The first one selected. The description could change to the corrected image. And also keep the other things same and run the code again to see the final results. And the previous results gets ready, and also I showed you how we can reduce its impact, the pixel impact from the first layer. As you can see here, the pixel impact didn't solve, and also we need to check something here. We did resampling before, but as you can see, when the result returned, we have the predicted with the original temperature that is not resampled before. Let me to replace it here, and now the problem will be solved and you can check the final result. Save it again and run. And the final result will be something like that between the corrected and original one. This is the difference, and here you can compare the differences. But this image related to the summer in which the water area included lower, the water pixels actually shows lower temperature, and also the barelands shows the higher temperature value. Also, this is the same as pattern of temperature you can see between you can see in the original temperature data. And now we will have this for the winter time. This is the corrected temperature that you can increase its contrast through the stretching technique. For example, I'm gonna increase it with 90% of values. So finally, visualization process is done and final result is ready. But if you want to spend less time of processing for the visualization, I'm highly suggesting you to get export from the results and using the export function I showed you before. And here, this is the winter time image that for 9070 for the January, you can see this is the corrected one and same temperature pattern with higher spatial resolution produced here. And here you go, and now you can use this data as a final as a new as an improved actually climatological variable regarding to temperature analysis for the next steps of processing. You can use this use this output for the next processing easily, but visualization process takes time. In that case, again, suggest you to get export and open it up into the desktop softwares. I hope you like this tutorial, and also the code link is available below this video on my YouTube channel. In the description box, if you had any question or problem, you can reach me out on YouTube channel and put your comment. And thank you for your attention.